Hello and welcome to this video. In this video we will solve problem number 161 to 170, and in the last video I could not explain the solution of 155, which was a brain fade moment for me. Apologize for that. So we will review the solution of 155, and before getting started I would request you to pause the video when I'm stating the problem, and only if you cannot solve the problem, then look at the solution. So without further ado, let's get started. So question 155, which we did in the last video, the statement is: find the necessary and sufficient condition on the natural number n for the equation x to the power n plus 2 plus x to the power n plus 2 minus x to the power n is equal to 0 to have an integral root. So that is what we need to do. Now, if you look at the solution, you look at this first paragraph. Okay, this is utter nonsense. You don't need to do this, but in exams, if you have the question, you need to do this way. But suppose we are just observing this function p of x. So this x to the power n, suppose n is a odd number. Okay, if n is odd, first we take n to be even. So if n is even, x to the power n will be positive. 2 plus x to the power n will be positive, and 2 minus x to the power n will be positive. So three positive terms will give us a positive value. That means it will never be 0. But we want it to be 0, right? So n has to be an odd number. Without n, it cannot be 0. If n is odd, this term can go negative and these two positive, and then, or this can also go negative, this can also go negative, depends on the value of x greater than 0 or less than 0. Suppose x is positive and n is odd, then this will be positive, this will be positive, and this will be negative. So there is a chance of becoming 0. So in the case of even number, there is no way it will be 0. Thus n is odd number. We don't need to do this calculation. That is one thing. Now suppose px is odd, then this will be an odd number, and this will be odd number because odd plus 2 is odd, and this will also be an odd number. But our px has to be 0, that is, it has to be an even, so x must be even. So this is the line of second paragraph which I could not explain. So you can see that how the rest of the solution follows. So if you have not seen the solution in previous video, you could watch it. And this was the line I could not explain. So now we have explained it. So let's move on to question number 161. Question 161. So question 161 says that suppose that the value of ax square plus bx plus c lies between minus 1 and 1, where x lies between minus 1 and 1, that is mods are less than 1, where a, b, c are real numbers. Prove that mod of 2x plus b would be less than 4 for the same value of x, that is x less than mod 1. Sorry, mod x less than 1. Less than equal to 1, not less than 1. So we move on to solution of 161. Okay. So when x is 0, we substitute x is equal to 0 here. X is equal to 0 is an allowed value. So mod c will be less than 1. Okay. Now we set x is equal to plus minus 1. We get a plus b plus c less mod of that less than equal to 1, and mod of a minus b plus c less than equal to 1. So we have got two conditions. Now what we do conclude from these two is that mod of a plus c is less than equal to 1. Okay, and therefore mod of c is less than equal to 2. Because our mod c is less than equal to 1, so we put it here. We get mod of a less than equal to 2. Now consider that if a is greater than 0, okay, then 2ax plus b would be less than equal to 2a plus b, because x lies between minus 1 and 1. So 2ax will be less than 2a. Now we expand this and we get the result a plus b plus c plus a minus c. So c gets cancelled, 2a plus b will be less than equal to 1 plus a minus c less than equal to 1 plus 1 plus 2 is equal to 4. And minus 4 would be minus 2 minus 1 we write it that way, which would be less than equal to minus a plus c minus 1 less than equal to minus a plus c minus a plus b minus c, which would be minus 2a plus b less than equal to 2ax plus b. So that's how we solve question number 161. So it's a very easy problem. All the problems are easy in this set. Now we have a difficult problem. Find the polynomial p of x is equal to x square plus px plus q for which max of p mod of px is minimal for x in minus 1 and 1. This is a classic problem of Chebyshev polynomials. So we will look at the solution 162, right? So I will explain the second method because that is the simple. First method requires a lot of intuition, and you can go through it and see if you can understand the solution of first method. For the second method, let's say, so our polynomial is x square plus px plus q. So now if p is optimal, then if you see the graph of a quadratic equation in this range, it would be either upward or it would be downward. Okay, so it must touch the values plus 1 and minus 1 in an alternating fashion at 3 points. So if you have this kind of graph, the downward, the top one would be plus m and the two values on the minimum side would be minus m, or if it is this way, then it would be minus m here and plus m here. So if this is what we have said that the graph must touch the values plus m and minus m. Otherwise, we could shift the polynomial slightly up or down and reduce the maximum absolute value. Now, the three natural points we can take in this range is minus 1, 0, and 1. So we write the values of those. We try p of 1 is equal to plus m, p of 0 is equal to minus m, and p of 1 is equal to plus m. Or you can reverse the sign also, it does not matter. So now p of 0 is q, p of 1 is 1 plus p plus, this should be q. Okay, it's a typing mistake. This should be q. And p of minus 1 is 1 minus p plus q. Now you solve this, you will get p is equal to 0, m is equal to half, q is equal to minus 2. So polynomial is x square minus half. So 162, we have a typing mistake. 163 we see. So we have to find real numbers a, b, c for which mod of x square plus bx plus c less than equal to 1 for all l less than 1, and 8 by 3 a square plus 2b square is maximal. So we have 163, right? Yeah, 163. Now if we see this, okay, so we put x is equal to 1, we get mod of a plus b plus c less than equal to 1. We put x is equal to minus 1, we got a minus mod of a minus b plus c less than equal to 1. So from these two we get mod of c less than equal to 1. And like one of the problems we solved here, this problem, right? Yeah, 161. So it's a similar problem. So from these conditions, we have got mod of a less than equal to 2, like we did in 161. Now we'll see why mod a is less than 2 in another fashion as well. Now we have 8 by 3 a square plus 2b square is equal to 2 by 3 4a square plus 3b square, which is equal to 2 by 3 2 into a plus b whole square plus 2 into a minus b whole square minus b square is equal to z. That's what we let. Now if we compute f1 a plus b plus c, f0 is equal to c. Now we are given that mods are less than equal to 1, so mod of fx is less than equal to 1. So we can write mod of f1 minus f of 0 is less than equal to 2. So mod of a plus b less than equal to 2 and mod of f minus 1 and f of 0 is less than equal to 2, that is mod of a minus b less than equal to 2. Now, since we have mod of a plus b less than equal to 2 and mod of a minus b less than equal to 2, to maximize this, we will have to assume that a plus b is 2 and a minus b is also 2. But that cannot be. So what we can take is a plus b is, if you see that a plus b is less than equal to 2 and a minus b is less than equal to 2, if you want to maximize both, then b has to be 0. If b is not 0, then both cannot be maximized. In any case, we take the value 2 and from both the cases and put it here. And this, if you want to maximize, that is z, if you want to maximize, this will be 0. That is b will be 0. And therefore, we have mod of a less than equal to 2. We put here or here. So as I said, we will see again that mod of a is less than equal to 2. So we have got our a, we have got our b. So once we have that, we can put it here and it will be mod of 2 plus c less than equal to 1 or mod of minus 2 plus c less than equal to 1 according as a is 2 or minus 2. So from these two, we have got c is equal to plus minus 1. So in one case, it will be plus 1. In one case, it will be minus 1. So that's what the objective of the question was, to find the real numbers a, b, c. Now we look at question number 164. It says that let a, b, c in set of real numbers a less than 3 and all roots of x cube plus x square plus bx plus c is equal to 0 are negative real numbers. Prove that b plus c less than equal to 4. So we have the roots minus p minus q minus r, that is p, q, r greater than 0. So from Beta's relationship, sum of roots would be a, which is given as less than 3. And the coefficient b plus c would be pq plus qr plus rp plus pqr. Now from MGM inequality, we know that pqr less than equal to p plus q plus r whole by 3 whole cube, which will be less than 3 because p plus qr is less than 3. So this is less than 1. Okay, so we'll use this for pqr being less than 1. Okay, there is no other use of this inequality. Now we know that p square plus q square plus r square greater than equal to pq plus qr plus rp. How do we know that? You bring it to left side and then you have half of p minus q whole square plus q minus r whole square plus r minus p whole square, which would be greater than equal to 0. So this inequality is established for us. Now we add 2pq plus 2qr plus 2rp on both sides. We get p plus q plus r whole square greater than equal to 3 into pq plus qr plus rp. And p plus q plus r is less than 3. So we substitute 3 and we get pq plus qr plus rp less than equal to 3. Now we add pqr on both sides. And this is what is b plus c. And we add plus 1 here because pqr we have established as less than 1. So this 1 will be added here and thus b plus c would be less than 4. So now we move on to question 165. Question 155 says that x into p of x minus 1 is equal to x minus 30 p of x. For all x in set of real numbers, find all such polynomials px. So this is a very straightforward problem. We set x is equal to 0, p of 0 is equal to 1. P of x is equal to 0. Okay. So there is a typing mistake. This should be 0. Okay. And we set how it is 0 is you set x is equal to 0 here. And this would be minus 30 and this would become 0. This x is 0, so it will make the left hand side 0. Similarly, if you put x is equal to 1 here, so this will become p of 0. Now p of 0 we have proven as 1. So p of 1 would be 0. So we continue till 29, we find p of 29 is equal to 0. So we let p is equal to x into x minus 1 into x minus 2 up to x minus 29 to qx, where qx is some polynomial. Then what we have is x into x minus 1 into x minus 2 into x minus 30, q of x minus 1 is equal to x into x minus 1 into x minus 2 x minus 30 up to qx. Okay, so we substitute p of x to the left side and to the right side, and then we have q of x minus 1 is equal to q of x, that is q of x is periodic. So q of x is equal to constant c, where p of x is equal to cx into x minus 1 up to x minus 29. Question 166 says that find the polynomial p of x if it exists such that xp minus 1 is equal to x plus 1 p of x. So you observe that p of 0 is 0, p of 1 is also 0, p of 2 is equal to 0, and so on. So up till infinity, we will find that p of x is equal to 0, thus it has infinite number of roots, and therefore p of x is equal to 0. Question 167 says that let f of x be a quadratic function. Suppose f of x is equal to x has no real roots, then prove that f of x is equal to x has also no real roots. So this can be a counterintuitive problem, but we'll try to make it easy. So the solution is by contradiction. Suppose f of x is equal to x has a real root, a is equal to 0. So what will happen is f of a is equal to a. Now suppose that f of x is equal to b, then it won't be equal to a, because f of x is equal to x has no real roots. So when this has no real roots and this is real roots, this is what we have established. Without loss of generality, we may assume that b of a greater than a. Then f of a is equal to b. Okay, we put x is equal to a. So f of a is equal to b. Now f of b, that is f of a, is equal to a. Now we consider a function g of x is equal to f of x minus x for all x. Now this is a counterintuitive step. You need experience to arrive at this function. You just can't magically get this. It follows that g of a is equal to b minus a. Okay, we put x is equal to a, we get g of a is equal to b minus a, which is greater than 0. And then we put x is equal to b. So g of b would be a minus b less than equal to 0, because if we put x is equal to b, so what will happen is f of b would be a. So a minus b less than equal to 0. Now you see the problem. Okay, we have f as a quadratic polynomial, so it is continuous. So what must be the case, because it is greater than 0, it is less than 0, there must be a root between a and b, because it is changing sign. All right, so but then that contradicts our assumption, and therefore both do not have real roots. Now we solve question number 168. The polynomial ax to the power 4 plus bx cube plus cx square plus dx plus e with integral coefficients is divisible by 7 for every integer x. Show that 7 divides a, b, c, d, e. So what we do is we substitute x is equal to 0, plus minus 1, plus minus 2. So when we substitute 0, e becomes 0, so which is divisible by 7. Now in remaining equations, I'll ignore e. We put x is equal to 1, we get a plus b plus c plus d is equal to 0, again mod 7. And a minus b plus c minus d will be 0. 16a plus 8b plus 4c minus plus 2d 0. 16a minus 8b plus 4c minus 2d 0. This is for plus 2, this is for minus 2. Now from these two equations, if we add those, we get a plus c is equal to 0. B and d will be cancelled out, and if we subtract, we get b plus d is equal to 0. A and c will be cancelled out. And similarly, from last two equations, we have got 4a plus c is equal to 0 and 4b plus d is equal to 0. Now from this equation and this equation, if we subtract, you get 3a is equal to 0. that is A is 0. Once A is 0 from this equation, C is also 0, and similarly B and D are 0 over here. And that's how we have proven that everything is divisible by mod 7. It's not that A, B, C, D are 0. It is equivalent to 0 when we divide with mod 7, when we divide with C. Now we come to the last two problems. Question 169 says that prove that a square plus ab plus b square greater than or equal to 3 into a plus b minus 1, where a, b are in the set of real numbers. So it's a one line answer. You just multiply the entire thing by 4, and then bring everything left to the left side and rearrange. You will see this equation, which will be greater than 0 because it's sum of two squares. Question 170 says that p of x is equal to x power 4 plus x cube plus x square plus x plus 1. Find the remainder of px to the power 5 when we divide it by p of x. So we have p of x to the power 5 is equal to x to the power 20 plus x to the power 15 plus x to the power 10 plus x to the power 5 plus 1. Now again it is a counterintuitive step. Remember, whenever you have to do something extra on your own, when you have to add something to the equations, something like this, okay, when we did g of x, f of x minus x, when you have to do something extra from your own side, it does not come from the problem. Those problems are very difficult to solve, and those are counterintuitive. So the objective of learning one of the part of maths is developing intuition by observing patterns in the problems. So what we do here is we rewrite this as, we add this minus x to the power 50, and x to the power 15 becomes 2, and then for x to the power 10 we have minus 2x to the power 10, and then it becomes 3x to the power 10, and so on. And once we have this is the product of x to the power 5 minus 1 into x to the power 15 plus x 2x to the power 10 plus 3x to the power 5 plus 4 plus 5. And then that is equal to f of x into x minus 1. So the question was px, okay? So if you see px is this, so this is equal to, now x to the power 5 minus 1 is f of x into x minus 1. So if you multiply x minus 1 with, px, this should be px. This is not f of x, px. Then you get x to the power 5 minus 1, and then we have this, and thus the remainder would be 5. Okay, when you divide, this term will cancel out when you divide by px, and we have remainder as 5. So with this, we come to the end of our 17th set of problems on theory of equations. I hope that you are enjoying the series, and I have tried to go slow in this video and explain everything clearly. So if you feel like it, or if you found the video useful, please give a like and subscribe to the channel. That means a lot to me. You know, a lot of effort goes in the videos, and when you subscribe and like the video, the reach of the video increases. I don't say this in the beginning of video because I don't want to divert from the matter. My first intention is to maximize the benefit to you. So if I say this in the between, that's a loss of time. That's why I say this at the end of video. The YouTube algorithm works that way, that the more the number of like and subscribe and shares, the more the reach. Shares are obvious, but like and subscribe also matter. And if you have questions, if you cannot understand any of the solutions, let me know in the comments and I'll try to answer those. So thanks a lot for watching the video. Enjoy.